Hello, so in this video I will show you how you can solve typical one-dimensional problems of the kind we have in the exams, but using ANSYS. Surprisingly, I think it's actually easier to do by hand than using the software, because the way the line elements are created is slightly confusing, and there's one step that is not necessarily obvious to do. But anyway, let's start. So we go into Design Model, straight on. XY plane, and we're going to sketch in there. Let's look at it. Sketching. Okay, so let's create three lines. First of all, maybe I want to be in millimeter. Yeah, that's fine. So three lines. Okay, one line. I'm going to look it on the origin here. Create one line. Okay, horizontal, coincident. A point to make sure it's coincident, and another one. Point and still horizontal and a point. Okay, great. That's fantastic. Now we'll dimension things. So that's three dimensions. One, come on. Dimension. One. Why not? One, two, three. Okay, three dimensions, which are 280 millimeter, 100 millimeter, and 100 millimeters. Great. That's that. Millimeter around, zoom, and that's that. Okay, so now from that, I want to create line bodies. So to create line bodies, you go into concept, and if you just use line from sketches, it will create a single line, but we want to have different cross sections as per the problem. So we're going to use line from points. So for my first line, line 1, I'm going to select that point, Control select the other point here, and apply it, and generate. That creates my first line here, and my part is created of this line body, and I will give it a cross section in a minute. Let me do the next line. So, to zoom a bit, I'm going to do concept, line from point again, select it, Control select the second point in green. Now just look at this operation. We've got two choices here. We can add material or add frozen. If we added material, and feel free to try that at home, it will actually merge with the first line. And we don't want that, because we want to be able, again, to attribute different cross sections. So you have to do add frozen. Okay, now that's going to create another part for that. But let's do it. Frozen and generate. Okay, so two parts, two bodies. All right. And finally, for the third one, okay, concept, line from points, and select that, Control, add frozen. I think add material might work here because it's separated, but let's be safe, makes no difference. Add frozen, generate. Okay, fantastic. So you three parts, three bodies. Now let's give it cross sections. Okay, cross section. I'm going to choose rectangular because it's easy to do the sums than a circle, and it makes no difference because these are just going to be trusses. So if I want a 400 millimeter, just 20 by 20 will do. And I will do the other two offline. So I have just done the other two cross sections, and now I can allocate them to line bodies. Okay, cross section, take them by name, rectangle 1, rectangle 2, and rectangle 3. Fantastic. If I want to visualize that, to see that they have cross sections, double check, I can always view and cross section solids. Okay, and then I can see the different cross sections. Okay, absolutely fine. Now that's all very good, and we should be able now to go to mechanical and to solve our problems. So we will do that and exit. Before we go into mechanical, it would be quite a good idea to create the new materials with the corresponding Young's moduli. So I'm just going to create different materials. I'm going to call M1. I don't like to type things. Okay, and of course, no properties, so just want them isotropic elastic. So click on that, and I can enter my values. The modulus, it's easier to type in megapascal. So megapascal, the material number 1 for the first step is 70 gigapascal, so it's at 70,000 megapascal. 1, 2, 3. Okay, need to enter Poisson's ratio 0.3, and makes no difference at all here. Could put anything. Okay, and the material is done, and we do the same for the other three. Okay, so in mechanical, I need to sort out the mesh. So the mesh, to do a very quick one, I simply said, okay, I gave in element size a large size, larger than the biggest element, and then it will mesh one element per beam. Okay, so I will look at it. I will also look at the statistics, and that give me, there we go, statistics. Now that's something I'm worried about, and it gives me 9 nodes and 3 elements. So 3 elements, that's fine. Okay, 1, 2, and 3. But 9 nodes, that's not too good. Now these are beam elements, so I know they have 3 nodes each. But what I would really like is that 2 elements, when the beam join, to be merged. I would expect, in fact, 7 joints. 7 nodes. 1, 2, 3, 4, 5, 6, and 7. But I get 2 extra nodes because it looks like here the two elements are not joined. Check that with connection, and there is nothing in it. So that's quite. It's possible to fix it by using some of the connection tool. That's quite messy. So, and in fact, if you try to solve that, you get all these errors, basically telling you that there are too many degrees of freedom, because indeed the nodes, these nodes are not joined together. So they can move way too much, all these elements. So that's not good enough. So I need to go back to design modeler to force it to be interested to be in single part. So if we check that, we have got line bodies are not together. Okay, so back in design modeler, and indeed 3 parts, body. We only want 1 part. So the useful command is essentially consists in creating a single part, assembling them together. So the way to do that is to select all the bodies and either go to tool, and then you get a form new part, or right click and get the same form new part. You can do that, and you get a single part composed of 3 bodies. Okay, and now we're gonna try to mesh and solve this in mechanical. I could say that the part can be broken again, and if it's needed at a later stage. But this create part is quite important if, for any reason, design modeler does not joins or bonds your solid object, be they solid, so be they beams or line elements or surface elements or solids. So when this is done, go back in mechanical, geometry, we've got 1 part composed of 3 bodies. And we can check the mesh statistics, and we see indeed that we have got, okay, yes, 3 elements, very fine, but it's only 7 nodes. Nodes here are merged, which is actually what we want. The connectivity has been done properly. Look at the connection, a bit more complicated, but let's not worry about that. Okay, so it looks like it has been done very nicely. Let's talk about the supports. Well, they're obvious, easy to install, easy to make. You've done them before. And let's look at the objects. The objects, solution objects. So instead of asking it to give me deformation everywhere, I just added deformation probe at the node, what we call node 2 and node 3 in the calculation by hand. And I also added force reaction at the 2 supports. Okay, so once it's solved relatively quickly, and we can check the values. The values at for the deformation, displacement, and that's given to us at 4.83 10 - 2 millimeter, 0.0483 millimeter, and the displacement here is 0.322 millimeter. And if we compare that with the solutions, we get exactly the same result, 3.22 and 0.0483. Likewise for the reactions, minus so a small one on that end, and a larger one, 45161, 4517. Oh, and small one, minus 483. It shows minus, okay, 483 here in Newton, and the answer was a bit Newton. Okay, so that's essentially what I wanted to show you. So the main information here is to be careful when you have got more than one part in your geometry, and that probably suggests that you might want to assemble one part in a design model. Okay, I hope this is useful. Thank you very much. Oops.